Right, how are we going? How we go? Oh, screen's gone blank. 23 people. Shall we make a start?
Yeah.
Yeah. Okay. Right. Hang on. Make sure nobody's coming. Right. Good evening, everybody. Tonight, David's going to do a talk about the universe in hydrogen alpha. It is clear, hopefully. If it is clear, David will set up his telescope. While he's setting up his telescope, I have a 17-minute video, how to image Jupiter, and then some of the free software you can use to post-process the images. But before we do that, there's just something I'd like to draw your attention to. Sidmouth Science Festival is starting soon. We've got the Family Science Day on the 9th of October. On the 11th of October, we've got Professor Glenn Patrick, who will be doing a talk on cosmic particles, messengers of the universe. That's on the 11th of October, 7:30 at the Parish Church in the Parish Church, not the Parish Church, sorry, in Sidmouth. You can book tickets via their website. What I will do though is probably in a week or two's time, I will send out the link so that for everybody to see, so that they can book the tickets. The tickets, basically, the booking system is just to make sure that they don't overbook because of COVID regulations and that sort of thing. But
is that
yes,
talk going to be Zoomed, Dave, as well?
I don't know, David. I don't know. I think it possibly will. I think there is talk to Zoom, all the talks as well as live. But Professor Glenn Patrick has specifically asked that he would like to, if possible, do the talk in person. So yes, he will be doing the talk. But yeah, I'll check that anyway, and I will email everybody, or I'll get Pete to email out a link nearer the time. Anyway, David, you've got control. If everybody'd like to mute and stop the video, then we'll hand over to David.
Okay, so can you all see that?
Yeah.
Charlie, good. Right, so yeah, I talked exploring the universe in hydrogen alpha. I've probably only been imaging in hydrogen alpha the last few years, so I'm fairly new at it. But for all those interested in imaging, it really does open up a new vista into what's out there. And I hope this evening my talk will show you how we can image in H alpha and the exciting sort of things that we can see. So first off, what is hydrogen alpha light? Well, of course, hydrogen is the most abundant element in the universe. At the Big Bang, it was 75% hydrogen and 25% helium with a bit of lithium. And of course, we know the sun and a lot of the stars are mainly composed of hydrogen. And hydrogen alpha is a specific, really deep red crimson spectral line in what we call the Balmer series of hydrogen emission, with a wavelength of 656 angstroms or 656 nanometers. And it occurs when the hydrogen electron falls from its third to its second lowest energy levels. And so right in the center here, you have the nucleus of the atom, and then you have these electron shells around it. So H alpha is a falling from the third to the second energy level in the hydrogen atom. And it's the brightest hydrogen line visible in our spectral range. And it is important to astronomers, as emitted by many emission nebulae, and also used to observe features in the sun's atmosphere, including, of course, solar prominences and the chromosphere. So here is what you would see in your spectroscope showing the Balmer series. The Balmer series was so named by the Swiss mathematician Johann Balmer in 1885 when he worked out mathematically the wavelengths of these different hydrogen lines. H alpha, as we'll see, has a wavelength of 6563 angstroms, and you can see it's in the red part of the electromagnetic spectrum. In a continuous spectrum, you'd have the, traditionally we have the shorter wavelengths of blue on the left-hand scale and the red, longer wavelengths on the right. And the transitions are named sequentially by the Greek letter. So the transmission from the third to the second energy shell is H alpha, the fourth to the second is H beta, the fifth to the second is H gamma, and the sixth to the second is H delta. And of course, the Balmer series plays an important role in spectroscopy and astronomy, and the spectral classification of stars depends on it as well. Probably the most, from the NLO's point of view, the most significant mention of hydrogen alpha comes with Lockyer's historic observations of hydrogen in the sun on the 16th of October 1868. When using his newly acquired spectroscope on his 6¼ refractor, he says, "I saw a bright line flash into the field. My eye was so fatigued at that time that I doubted its evidence, although unconsciously I exclaimed, 'At last.' The line, however, remained an exquisitely coloured line, absolutely coincident with the line C of the solar spectrum. This is a Fraunhofer line due to hydrogen in the red, and as I saw it, a prolongation of that line. Leaving the telescope to be driven by the clock, I quitted the observatory to fetch my wife to endorse my observations." And that was probably Lockyer's most famous discovery. He found a way of actually using his spectroscope to image the solar prominences outside of a total solar eclipse. So we see the Balmer series in spectrum of bright stars. These are A05 stars when they're the brightest, but these are actually seen as absorption lines. Here's an H alpha absorption line, this dark line here. Their lines of reduced intensity on a continuous spectrum. So the continuous spectrum is a background going from UV, violet, ultraviolet, violet, green and red, where the gas, mostly hydrogen, the outer layers of the star, absorbs some of the light from the underlying thermal back body spectrum. So we have a H alpha, beta, gamma, delta, epsilon, etc. Our eyes won't take us into the far UV. We can't see that far, but of course our imaging devices can see it. But we also see emission lines in hydrogen alpha. This is Lockyer's bright red H alpha line that he saw in his solar spectrum. And the emission spectrum is caused by an atom or molecule making a transition from a high energy state to a lower energy state, generally shown in the hot stars, the O and A and B type stars, and of course what we've seen in novae, more recently novae. This particular star, Delta Scorpius, is a rapidly rotating BE star. The E stands for emission, hence the H alpha emission, with a stellar disk showing these emission lines not only in H alpha but also in H beta. This is an emission line here, and these are the absorption lines, the dark lines. The dark lines at this end are called the telluric lines. This is due to water and atmosphere in the Earth's atmosphere. So here's some more emission lines of H alpha. This is a recent star I took a spectra of. RS Ophiuchi is a recurrent novae, approximately about 5,000 light years away. In its quiet phase, it has an apparent magnitude of about 12.5, so it's fairly faint, but it's been seen to observe to erupt on about 7 occasions, and more recently, just these last few months, where it reached about magnitude 5 on average. And it's caused by a white dwarf orbiting close to a red giant, with an accompanied accretion disk on the white dwarf, which when it material builds up every 15 years or so, it causes a thermonuclear explosion, and we get these bright and broad hydrogen alpha lines, H beta, but you also get the helium lines as well. This is the famous yellow helium line seen in the sun. Here's some more examples of hydrogen alpha emission in B stars. Famous one, of course, Gamma Cassiopeia, Phi and Psi Persei, and Zeta Taurus. And these are rapidly rotating stars with H alpha emission from the circumstellar disk orbiting these stars. Of course, Gamma Cassiopeia was very active in the 1930s, and many images and spectra were taken by Jim Lockyer using the Mond telescope. Graphically, we see this really lovely spike in H alpha and H beta in Gamma Cassiopeia. Comes out very well with an LP spectroscope, but you can also get the H alpha and beta with a simple diffraction grating on your camera lens. I'm going to slightly digress now. This is hot off the press. We received a postcard this morning addressed to Norman Lockyer Observatory. It was sealed up in a little envelope. I don't know who sent it, but it was addressed to Major William Lockyer, and it was dated April 10th, 1921. That's 100 years ago. And it was sent by the librarian of the Science College of the University of Tokyo, Mr. S. Nishikamba, the librarian. And he was sending thanks to Jim Lockyer for sending a copy of his observations of Nova Sig 1920 and presumably the handbook of the Hill Observatory, Salcombe Regis. Please note, it was at that time still named the Hill Observatory and not the Norman Lockyer Observatory. So what was peculiar about this particular postcard was the fact that it was sent anonymously, but it wasn't quite anonymous because there's a postcode on the back. It says number 13, GU28 OEU. Well, if you say that's a postcode, that postcode agrees to a property in Petworth in West Sussex. So I must try and find out who sent this, because he didn't send any covering letter. Alan mentioned today that there was an article on BBC News about a chap who's been sending out postcards he's bought off the internet and tracking who they were sent to and been sending them, and still have a big follower of grateful people who received these old postcards. So he might have been the person who sent this, I don't know. We haven't got the end of this particular story. But what I thought I would do, because it's sort of relevant, it's a nova explosion happened in 1920, and see what Jim Lockyer's observations of this star was. And in fact, if you Google Nova Sig 1920, the first thing you come up with is Jim Lockyer's observations. And it's rather wonderful. It's paper written by himself and Don Lebowitz. And it's a comprehensive report covering several months of daily observations and spectral images of this star. And he writes, on the afternoon of August the 21st, a telegram was received at the Hill Observatory, Salcombe Regis, from Brussels, informing us of the fact that Mr. Denning, he was a great variable star observer at the time, had discovered a new star in Cygnus of magnitude about 3.5 and giving its position. That evening was cloudy, so observations could not be made until the evening of the 22nd. And since that date, a large number of photographs of the spectrum have been taken and determinations of magnitude made. It is the object of the present paper to present some of the first results from a discussion of the observations and photographs obtained. Well, I'll give you the link, you'll be able to read it all. But what is also really significant about these observations, and they were carried out just 5 days after the passing of Norman, who died on the 16th of August that year. This is 1920. They must have thought that Norman had taken his place in the heavens as a new star. And this is his observations of the light curve. And you can see it reached magnitude 2, so it was a really bright star, but it quickly faded off. By middle of October, it was back down to magnitude 9. But what was also amazing about his observations is look how many clear nights they had in the late summer of 1920. From August the 22nd, almost daily, right through September, just a few, the 7th was missing. Every night was clear until early October. So they took lots of spectra of it. And he says, in general terms, the spectrum at this stage may be described as being almost identical with that of Alpha Cygni. It possessed a continuous background with fine, sharp absorption lines of hydrogen, silicon, and enhanced metallic origins, which corresponded to all the principal lines of Alpha Cygni, except for considerable displacement of all lines towards the violet. So they were seeing that it was being blue shifted, this material was coming towards them. Then he notes there was several important changes in the appearance of its spectrum when the nova was near the apex of its light curve. This occurred on August the 24th, and photographs were taken on that date which showed that the absorption lines were all broader and more diffuse than August 22nd, and there was a considerable increase in the displacement towards the violet. When the nova was well down on the descending part of its light curve was reached, it was generally described as a typical nova stage, and there was a considerable increase in the intensity of the bright lines. So these are the emission lines, which at this stage were fully as conspicuous as the absorption lines. Plate numbers 1, 5 to 6. So here is the actual photograph they took, but please note, in those days, their photographic plates weren't at all sensitive at the red end of the spectrum, so they could only image from H, beta, gamma, and delta. But here you can see it starts off with the absorption lines, and by here you can see the emission lines appearing in the nova. So I thought that was a little digression about the little postcard that I received today. So we talked about hydrogen alpha emission in stars. What about planetary nebulae? Well, in Lockyer's day, I'm talking about the elder Lockyer, they didn't really know whether planetary nebulae were clusters of stars seen at a great distance where you couldn't resolve the stars, or whether they were gaseous in their content. And the problem was solved by William Huggins, who identified bright emission lines of hydrogen in the planetary nebula NGC 6543, and he was able to show that these were gaseous bodies and not made of stars. And he identifies hydrogen alpha and H beta, but other bright lines adjacent to H beta, these lines, he didn't know what they were at that time. He called them nebulium. He thought it was a new element which hadn't been seen on the Earth, but it wasn't until 1920s when they worked out this was actually an excited state of oxygen. This is O3 emission, which can only appear in conditions of very low pressure. And here's an image I took recently of the Cat's Eye Nebula, showing the extensive emission. Visually, we see the digital part here, but the L-enhanced filter that I used to take this picture shows the enhanced O3 emission out through here. Here's another deep red line, but this one is not hydrogen alpha. This is actually a helium line, which is very close to the H alpha line. And this star, Wolf-Rayet 136, is a central star in a popular target for astro images. This is the Crescent Nebula in Cygnus. This is a very hot star. It's about 600,000 times brighter than the sun and a lot more massive. And it has a surface temperature of about 70,000 Kelvin. So it's a really hot star. And it's blown off the shell. And here is a spectrum showing the bright helium emission lines. Now, using a wider field, this is the Crescent Nebula. I was using a wide field telescope. I recently bought a little red cat, which just has a diameter of 51 millimeters. It's quite a small telescope, but with a 7 nanometer H alpha filter, it allows wide field shots of the sky. And here you can see the bright emission, H alpha emission, and extending right out into the surrounding area. And that's the Red Cat 51. So nicely engineered telescope. Again with the Red Cat, here's another famous H alpha emission region, the famous North American Nebula. This object here with the Gulf of Mexico. And next to it is the famous Pelican Nebula. And there's his beak, and there's his eye, and there's his body. Now the beauty about H alpha imaging, you can carry it out under bright moonlight. This photograph was actually taken under the night of a full moon. The H alpha, of course, will cut out all extraneous lights, earth glow, moon glow, street lights. So it's a really useful technique to use if you've got light polluted skies. And you can put some color with it. Here it is in a red hue. Here's another interesting region about the central star in Cygnus, Saturn, showing dark, dusty material, blocking out the starlight from behind. And these images were taken with a mono camera, but you can also use a one-shot color camera with a special filter to enhance hydrogen alpha. So you're not restricted just to mono camera. And what I've used now is what's called an L-enhanced, Optolong L-enhanced filter, which here it shows H alpha, but it also includes this line here, which is O3 and H beta. So it will block out sodium street lights, mercury street lights, and a lot of the sky glow. So again, it's another useful filter arsenal for our telescopes. And this is North American Nebula taken with, again, with the N-enhanced filter. This is 20 by 120 seconds. And so most narrowband filters, you can get different ones. They're designed to let in one particular wavelength of light, such as H alpha, O3, or sulfur 2. And I said before, the L-enhanced filter is a dual band narrowband filter that blocks out most wavelengths. So it's very useful with one-shot color cameras. Just showing how effective it is, here's a comparison of the Eagle Nebula. This is M16. This is imaged just with a one-shot color camera, 20 by 120 seconds, with an ASI 533 color camera. Here you can see the famous eagle with his wings. Again, was the red cat, so it's quite a wide field of view. But here's the same target imaged with the same exposure time with an L-enhanced filter. So you can see it's enhanced all the bright red hydrogen alpha, which you can barely see in this image. What you also know, of course, it shrunk the stars. The stars are a lot more tighter in hydrogen alpha light than they are in the broad spectrum of starlight. Other H alpha targets is a famous Veil Nebula in Cygnus. And you see in particular the two colors. You've got the red from hydrogen alpha, but you also got the green. This is the O3. And quite often we put an O3 filter on the Connaught telescope, and you can see visually these beautiful filaments around the star 61 Cygni, visually through the eyepiece of the Connaught with an O3 filter attached. So it really does look like the photograph you'll see in H alpha and O3 images. Here's a little GIF showing the famous Crab Nebula, first of all in monolight, and then in the light of hydrogen alpha, showing how it enhances views of the filaments. And here I've combined a green and a blue filter with H alpha taking the place of red, and showing how these filaments are extenuated. And the filaments are the remnants of the progenitor star. Remember this star the Chinese saw explode in 1054. And these filaments are composed largely of ionized helium and hydrogen, along with carbon, oxygen, nitrogen, iron, neon, and sulfur. And the whole thing is expanding about 1,500 kilometers per second. People have recently taken shots of the crab imaged probably about 10 or 20 years apart, showing how you can see visually how these filaments have extended over that time period. The N-enhanced filter is also very useful in detecting very faint planetary nebula. This is a very faint and large object. This gained image with a red cat. It's not visible to your eyes through a telescope, but it's a planetary nebula in the constellation of Gemini, originally discovered in 1955 by Giorgio Bell, who classified it as an old planetary nebula. They weren't quite sure of its origin at the time, but they now think it is a planetary nebula rather than a supernova remnant. When looking at galaxies, of course, M82 is a nice bright galaxy. It's actually a starburst galaxy. So it's about 12 million light years away in Ursa Major. It's a member of the M81 group, and it's about 5 times more luminous than the Milky Way, and has a center about 100 times more luminous than the Milky Way. But if you put H alpha, or include H alpha exposure with the G and the B filters, you get this wonderful sense of an exploding, you can see why it's called a starburst galaxy. The other thing you can look for in galaxies is what we call H2 regions. This is the pinwheel galaxy M33 in red, green, and blue, but you can see there's this hint of some red patches in the spiral arms. If you image it with an L-enhanced filter, these H-alpha regions pop out. And these H-alpha regions are a region of interstellar atomic hydrogen that's become ionized. It's typically a molecular cloud of partially ionized gas in which star formation has recently taken place. The density ranges from a few to about 1 million particles per cubic centimeter. This bright one here, NGC 604, will be a lot larger than the Orion Nebula. And of course, the Orion Nebula is one of the brightest H-alpha emission sources visible to the naked eye. But of course, we see it through our telescopes the best as a greeny color rather than the red H-alpha, which the camera picks up. Eyes aren't sensitive enough in color to pick out the redness of the Orion Nebula. So this is a huge bubble of gas, probably the mass about 2,000 suns, and quite a few little protostars with circumstellar disks around them, which of course you've seen from the Hubble Space Telescope. Here's another bubble. This is the famous bubble nebula, NGC 7635. Smaller than Orion, it's just 7 light years in diameter, is illuminated by a hot O-type star. I'm guessing it's this one. Again, it's about 7,000 light years distance, so a lot further away than the Orion Nebula, hence it's a lot smaller. And that was imaged with the C9 telescope and L-enhanced filter. So what about H-alpha imaging in practice? Well, you can get a large one, a 2-inch H-alpha filter. They're a bit more expensive, and they could be mounted in front of a camera lens for wide field imaging. So you can put it in front of your 50mm DSLR images and get nice wide field images of Orion. You can probably show Barnard's Loop with that, and of course all the extensive nebulosity around Orion and the Horsehead Nebula. You can put it in front of your CCD for imaging through the scope, and then you use a little 1.25" filter. But it is, of course, a deep red filter, so you need longer exposures. You need typically about 5 minutes per sub each exposure. Therefore, you do need to auto guide with using H-alpha filters. So you need a separate guide scope to do that. If you're using imaging through a camera, it's hard actually to see the target.
I think David's froze. Oh,
so, hello, can you hear me?
yes, you'd frozen, David, for a minute, but you're back now.
Okay. So as I say, it's hard to see if you're on target with short exposures, but it's worth persevering. You'll soon get the hang of it. And it's a benefit. The stars appear much smaller and tighter in hydrogen alpha, which gives very impressive wide field views. So in practice, the filter blocks out all unwanted light from artificial light pollution, from natural air glow and moonlight. And it blocks all the sodium and mercury street lights. The two versions, there's a shorter wavelength, the 6 nanometer and the 12 nanometer. Both are 100, and the shorter the wavelength ones are a bit more pricier than the longer ones. So that's imaging the stars, but of course, alpha light is also emitted from the hydrogen atoms in the sun. Of course, the sun is composed mainly of hydrogen. And when the electrons from those atoms absorb energy and rise to a higher energy level or orbit. When they cascade back to their original orbits, they release that energy as a crimson light with a wavelength of 6563 angstroms. To safely view H-alpha emission from a sun, you need a dedicated solar telescope. And this is the one I've got, a 70mm solar scope attached to standard William Optics 100mm scope. It consists of two filters, the red pre-filter on the front of the scope and a second energy rejection filter, this one in here, at the other end, prior to the camera or eyepiece. I've got the camera on the end here, but I've got a flip mirror so I can see the target safely using this little eyepiece. And there's a little mirror switch here you can flip so the light goes to the camera. And what is wonderful about H-alpha imaging is you can see prominences, spicules, fibrils, element bombs, flares, all seethe and boil before your eyes. And the process occurs with great efficiency in this thin band here, 1,250 mile thick layer of solar atmosphere, which Lockyer named the chromosphere. Here the temperature rises from about 11,000 Fahrenheit to about 36,000 degrees Fahrenheit, hot enough to excite hydrogen and to emit its singular red light. Now, a lot of the solar prominences we can see can be classified. You get the quiescent ones. These generally last for a few days, or you get the eruptive ones, these ones down here. A large quiescent prominence here. This one was imaged, could be seen for about 3 or 4 days on the limb of the sun as it rotates around. And then when it rotated around, you saw it as a dark filament. This is a fine looped eruptive prominence, imaged 19th July 2012, showing actually raining plasma back on the sun. And of course, all these hot plasma is kept in these beautiful arcs by the magnetic field lines, these intense magnetic fields rising up from the sunspots. This is an eruptive prom. These are very short-lived, probably last a few hours. This one's called a surge or a spray prominence. You can see it erupting here. They aren't particularly large objects. You see them as little spicules. Here's a solar flare, May the 7th, 2013, a sequence probably imaged over about half an hour, showing a sunspot with a nice light bridge and a bright solar flare kicking off. We often see these light bridges across sunspots. This is a sign that the sunspot is about to break up and subside, but there can be quite spectacular features. Here's another one of the heart-shaped, lovely heart-shaped sunspot. Lockyer himself drew a sunspot this shape way back in the 1860s. And the following day, it revealed a C1 flare. This is a major sort of flare on the sun. And all these sunspots are named, they're called AR, stands for active region. And as they rotate around the sun, they're named in sequence. Some eruptive prominences can extend for many thousands of kilometers above the sun. This one reached about 200,000 kilometers, half the Earth-Moon distance. And here's a picture of an eruptive prominence that actually lifted off the solar surface. This was imaged just a few days ago on the 12th of September. You see it's actually taken off, and this one has given rise to what we call a coronal mass ejection. And here we've got approximately 1 million tons of hydrogen plasma traveling at 1 million miles per hour. And of course, if the Earth gets in the way, we get to see the beautiful aurora. This was a picture I took in November 2014 from Iceland, from the Thingvellir National Park. Of course, you've got an aurora on the screen behind me, and although they are impressive, they're not visually, they don't appear as rapidly as they're changing in this background image. But you're certainly aware of these streamers changing after a matter of a minute or two. And on that note, I will end. But it's not quite the end, because I've got a few other pictures I'll show you before I go out and open up the telescope.
Okay, thanks, David.
Here,
Brilliant presentation, brilliant.
we might be able to have a look at some of these tonight. Here's an image a few nights ago, Neptune and its moon Triton, and there's a lovely contrasting star it just passed. This is K3 yellow-orange star. It's moving this way, so it probably won't be in the field tonight, but we can have a look at that. Uranus and its 5 moons, Titania, Oberon, Umbriel, Ariel, and this one here is Miranda. So you should be able to pick up 5 moons with a dedicated CCD camera on a telescope. More recent images of Jupiter. Here is the, move the screen up here. This is the occultation of Europa, popping behind Jupiter, and the eclipse reappearance of Io. It was coming out this way. It popped out here to see the distance is increasing. Nice little white ovals in the south temperate belt up here. And one last request. We hope to be live streaming the planets, Jupiter, Saturn, our moon, and much more from telescopes for Sidmouth Science Festival on the 12th, 13th and 14th of October from 8 o'clock. Dave Alexander will be our host for the evening, and we do hope you can join in, get some telescopes, live streaming the planets for an hour or so. Happy to run a practice session. We'll are going to have a go tonight and see if it all works, of course. But do come along to this if you can live stream. I know people like John McLean and Mike Curran, you can do it. So let's have a go and do some live streaming. And on that, I will finish.
Excellent.
Fantastic.
David.
Thank you, David.
Yes, really good. Really good.
Thank you, David.
Fascinating.
I'm not sure how good it is where you are, David, but I've got thick cloud here now. I can't see a thing.
Let me just pop out the door and have a look.
Okay, I better look out here, and I can see stars.
Well, I can't see a thing. The clouds are in the way.
I've got clouds here as well.
Hi, Samantha. Yes.
Hi, Dave.
Yes, it's still clear here, so I'm going to go away and set up.
Oh,
Dave,
show
you
this video then.
Yeah.
This video is 16 minutes, how to image Jupiter and how to process it. So I'll run that while David's setting up. Okay, here we go then. Come on, Dave. So we need to share sound. Come on. It's just going to take a minute. Always seems to take a time. Probably my wife watching the Scandinavian murder mysteries. Oh, no. Can we hear that? See that?
We can.
Okay,
Free
Dave.
processing
Yeah, Roger,
tricks
Roger.
you can use to clean your AVIs up
and then we'll go through
Oh no, it's the wrong one.
registration.
I don't believe this. I've got the wrong one. Sorry, everybody.
Go and get
Pay
the stuff.
peanuts, you get monkeys.
Oh, blimey. Hang on. Hang on. How could I do
And,
it? Oh, hang on. We don't want that.
Also a little bit of Photoshop edit maybe at the end.
This one's the rubbish one.
But anyway, let me show
Right. Let's get the start again. Blimey. Do you know, I spent ages getting this ready. I haven't got it. I haven't got it. After all that, oh, bloody hell.
If only it were Friday the 13th, you'd have something to blame it
Yeah, I
on.
know. Gosh, after all that, I've got the wrong one, ain't I? Yeah, it's the wrong one. Hang on. What have I? Gosh. Hang on. Here we go. Here we go. This is the one I want. This man.
Hey everybody, it's Michael again with Late
Can
Night
we see
Astronomy,
this one?
and I'm out on a beautiful
Yeah,
night
All
Roger.
good.
with my favorite
Right,
planet,
okay.
Jupiter. Its cloud belts, great red spot, and Galilean moons make it a unique target every single night of imaging. In today's video, we're going to take a look at the basic steps that you need to take to capture footage of Jupiter and process it using free software so that you can create incredible images of this planet to share with your friends and family. If you enjoy this type of content, please consider liking this video and subscribing to this channel. And most importantly, let me know about your questions and experiences imaging Jupiter in the comments section below. Let's get started by connecting our equipment to our telescope. For tonight, I'm going to be connecting my DSLR directly to the telescope using a T-ring and extendable camera adapter. At the end of the extendable adapter, I'm going to connect a 3x Barlow lens. You may want to consider a 2x Barlow lens depending upon your telescope and imaging equipment. This Barlow lens will provide proper focus for my telescope and image sensor, along with tripling my focal length to bring out more detail in Jupiter, particularly during evenings when sky conditions are clear and steady. If you're using a smartphone, simply connect your smartphone to a camera adapter and place the lens of your camera over a medium to high power eyepiece to capture your footage of Jupiter. Set your DSLR to manual and open up the main menu. Make sure that your camera is filming at the highest frame rate available, which for this model is 60 frames per second. I've also got my shutter speed set to 60, and I've found that good ISOs for Jupiter tend to range from 800 to 3200 for this specific camera. It just depends on the sky conditions that evening. Be sure not to forget to change the picture style to neutral and the white balance to daylight. Now that our settings are locked in, let's switch over to live view to find the planet. Once you have found Jupiter with your telescope, you will need to use the digital zoom feature at 5x or 10x magnification, and as the object moves through the field of view, make fine-tune adjustments to your telescope's focus until you are pleased with the sharpness of it. Now reset your telescope to allow Jupiter to move through the entire field and press record right as you start to see it appear. Be sure not to touch anything while it is recording. I typically like to get at least 10 passes at a planet, trying out different ISO settings along the way. Just be sure to always double check your focus. Once it passes out of the field of view, stop the recording and review your footage. After a great night out imaging and viewing Jupiter, we're back inside for the next step of the process. This is going to involve 4 free pieces of software that I'll be sure to leave a link to in the description below. Through this software, we're going to process, stack, and enhance this footage of Jupiter to bring out some incredible details. Let's get started. Well, the first thing we're going to want to do is begin by reviewing the footage that we actually took of Jupiter. So I've got my folder up here already organized into the 3 best ISOs that I got for imaging. ISO 800, 1600, and 3200. For tonight, it was a little bit overcast, and the ISO 800, as you can see, came out just a little bit too dark. It's almost actually impossible to see right here. If we go over to ISO 1600, we have a much more recognizable view here of Jupiter, and we can actually make out that we got the red spot tonight. So that's pretty cool getting the great red spot. I did not know that was going to be visible this evening. But that's still a little bit too dim for the conditions that we had tonight. So most nights I probably would go with 800 or 1600, but I think the ISO 3200 footage is really going to be the sweet spot this evening. Yeah, that's an excellent view of Jupiter that we have, and it looks to be pretty clear and steady skies for this roughly 45-second clip that I got. So we're going to go with this one. So we've got the ISO 3200 footage, and the first thing that we're going to have to do is run it through a program called PIP, Planetary Imaging Pre-Processing. This is going to make sure that the footage is able to be used for every step to come. So I'm going to go up here to File, click Add File, and it's already here in the folder where I've got the ISO 3200 footage of Jupiter. Now you're going to want to make sure that you click on Planetary, because that's what it is. We're shooting the planet Jupiter. And there's not much else that I'm going to change in terms of what is already here. The footage that I have tonight is pretty straightforward. It's Jupiter just moving across the field of view, so I'm not going to have to do too much to it. Just to be sure though, make sure that you've got your output set to AVI and that the AVI file option is raw uncompressed. Things different than that I've had trouble with in the past. So from that, let's click on Start Processing. So PIP has worked its magic, and just to make sure, let's go look and see what it actually did. So we go back to our Jupiter folder. We now have a PIP folder here, and we can see that our image of Jupiter that used to have it moving across the field of view has now been centered. So we have Jupiter that is framed, that is in the right format to be used for all of the steps left to go. So that's exactly what we want to see. So I'm going to close out PIP and go to our next free software, which is AutoStacker 3. I'm going to begin by opening up the file that we just looked at here. Go to the PIP folder and then bring that into the software. You can see it framed here very nicely. We're going to go over and we're going to click Analyze. Now this is going to go through and basically judge the quality of each of the roughly 3,000 frames that were captured earlier in our video. And we've got some pretty good data here. So if you go over here, you'll see to the far left that this is going to be the highest quality frames, and then over here to the right will be the lowest quality frames. So the question then becomes, how many frames do you want to have in it? Do you want it to be something like 25% right here, 50, 75? It's going to be a judgment call depending on your footage. If you see a dramatic spike down at any point of the curve, that's where you're going to want to stop it. So I definitely wouldn't want to go over here and do 100%. But this is pretty good footage, so I think I'm going to do something like 90% of the frames being kept for this, just to see how it turns out. So once you've determined that, you're going to go over here to this window, and you're going to want to place the alignment points so that it knows exactly what it's looking at. So let's do place AP grid. All right, that's a pretty good starting point. You can adjust the brightness here to maybe get more of them or fewer of them. It depends on how bright your object is, but that looks pretty good. We could go up here and make the alignment points smaller, but you really don't want to have too many alignment points. I found that most of my best footage ends up being somewhere between 20 and 30 alignment points, because you really want them taking up a good amount of the surface of the planet and overlapping each other so that they know what they're doing when they're stacking it. So I'm pretty happy with this. We've got 26 alignment points. They're at size 48. The brightness is at 10. I think this is going to go pretty well. So let's stack this footage of Jupiter. All right, so Auto Stacker 3 has run its course. Let's go over here and check on the picture. So we started out with this video of it moving across. We had that stationary with pip, and now we have this new folder here, Auto Stacker 90. So this should be 90% of the best frames stacked into this image. That is already looking like a better image of Jupiter. That's a pretty good start at this point. But I think we can make it even better than that. So let's go into now Registax 6. And this is when really the magic happens in terms of bringing out detail of it. So we're going to go to the file that we were just at, where we have the 90% of frames that are stacked. And we have this much brighter image now of Jupiter. And there are a few things that we want to do at this point. The first is we want to make sure that our colors are aligned. So we're going to go over here to RGB Align. Let's click Estimate. Okay, so that's shown us that there was a little bit of a difference that it did in terms of the colors, so that's good. So that's a little more aligned of an image. Next thing I like to do is RGB Balance, and this is going to be a pretty dramatic difference probably. Let's click Auto Balance. That is a very big improvement. Much more natural colors. Let's go up here to histogram. So the histogram can be confusing. The first thing I normally like to start to do for an image like this is cut it off at the end right here. Maybe around 20 or so. So let's click Stretch for that. Okay. So that brings out a lot more of the histogram curve now. You may want to leave it where it is. You may want to move it in a little bit. I like typically having some room to work with the histogram at the end. So I'm actually not going to do anything else other than that first adjustment. But I am going to leave this loaded up in the corner because it can tell us some good data as we're going into different parts of this. So let's go over here to wavelets. Wavelets are incredibly powerful and incredibly confusing as to how they work. You'll find a lot of different tutorials on a lot of different websites that'll show you techniques. I've found that every single time I'm using wavelets, I use them a little bit differently depending on the planet, depending on the quality of the image. So this is something that you're going to really want to experiment with to get out different versions of your planet. But I'll walk you through a basic workload of what I do. So I start by taking layer 1, and I'll bring it over here to maybe about 75%. And we already start to see some pretty good detail coming out of the planet. I'm going to push the sharpness up just a little bit, maybe to 1.2 or 0.120, excuse me. As I'm doing that, we're starting to get a little bit of noise. So I'm going to go over here and click the denoise, maybe up to 0.20. Second slider, I'm going to bring layer 2 over to maybe 50%. And again, I'm going to go and sharpen this a few times, but also get rid of some of the noise by denoising it as well. Layer 3, we'll do that around 50% as well. Maybe bring that up a little bit. I'm pretty pleased with that. You could spend all day going through doing the sliders in different ways, but just for the tutorial right here, I'm actually really pleased with how that turned out just from those steps. And you can see as I unclick here what we're talking about in terms of the difference. This is the original stacked image, and then we add layer 1, layer 2, layer 3. I'm pretty pleased with that. So let's go ahead and save this image. All right, we'll save this as Registax Jupiter. All right, and we'll X out of this. So now we're going to go to the final step, and that's going to be with GIMP. Now, some of the color corrections I'm doing here you can do in Registax, but I found that actually using this program gives me results that I think are a little more pleasing and a little more accurate. So we'll go in here to our Registax Jupiter file that we just finished with, and we'll pull that up. Now, there are two main things that I do here in GIMP, and they mainly involve contrast and saturation. So I'm going to go down here to brightness and contrast and just maybe push that up a little bit, just to maybe bring out some details. That might be a little too much. Let's bring that back a little bit. Yeah, I like that. That looks good. And let's go up here to saturation, just to bring out some of the colors that are already there. Got the cloud belts showing up, how wavy and different they are, the great red spot. Yeah, that's good. It's always a balance between finding something that looks natural and not overly processed. That's going to be the biggest trick for all of these steps, is making it look natural and not overly processed. Let's click OK. I'm pretty pleased with that image. Let's go over here and we will export this as a TIFF file or JPEG file, whichever you prefer. We'll do a TIFF file of Jupiter final image. From our original video of Jupiter to this final image with the cloud belts and the great red spot. I hope you all have enjoyed this tutorial and it's been helpful for you. Jupiter is by far my favorite planet to observe and image, and the incredible unique features of the surface of this planet that we see in this image hopefully tell you exactly why that is.
Oh, blimey. Well, I hope you found that interesting. There was three things that I picked up on that. The first, that he was quite happy for Jupiter to track across the screen. I always thought you had to your telescope had to track it, but he wasn't worried about that, which meant to me that you could image Jupiter on an ordinary tripod.
Yeah.
Yeah. The second thing was the use of wavelets on Registax, because that is the first time that I'd seen that so clearly explained to me as to what was happening and the best way to approach it. And finally, I don't know if you noticed, when he was finally processing the image in GIMP, he was using the preview button and he was clicking it on and taking it on and off so you could see the image before and after you'd applied, which I thought, I never thought to use that. So yeah.
Learned a lot from that. I didn't realize you use 4 separate sort of programs, really: the PIP, the Auto Stacker, the Registat 6 and the GIMP.
All 3 as well, Howie. So I'm going to say Alan Smith's on here tonight. He the first person to introduce me to PIP, but I'd never heard of PIP before. But yeah.
Well, thank you very much.
Yeah, PIP is very useful. I think though what it shows is, even if you don't want to go through all the screens and scratch your head about all the various settings, you can just load up the file and it'll make a pretty good job at it.
Yeah.
You haven't got to be too scared of these things. The kind of defaults that you get will produce a reasonable file.
Yeah.
But recently I had a bit of time to kill on one particular afternoon, and I did go back to some older video that I took, and I went through a lot of the other screens and the other parameters and just tried them out to see what else you could do.
Yeah.
And the thing they're relying on, what he's relying on, is there's a section on one of the screens that deals with how it identifies where Jupiter is.
Right.
It's called object detection.
Hmm.
And what it's doing is it's looking for that where Jupiter is on your frame,
Yeah.
and always bringing it back to the center. And you've got
Yeah.
to set that at the right level. If that's not sensitive enough, it won't spot where Jupiter is.
Right. Okay.
So there's a couple of things, extra things you can do.
Yeah.
The other thing I found is that I was always filming a full frame, which means you've got an HD frame, 50 of them a second, and you
Yeah.
end up with massive files.
Yeah. Yeah.
And again, you can set how it crops Jupiter so that you're not saving great big video files. You're
Yeah.
just saving that little bit in the middle where Jupiter's sitting.
Yeah.
Yeah.
It was also
Yeah.
interesting in the Registrax, the use of the RGB align as well. You know, which I thought, yeah.
I have played with that. I wasn't convinced that what it suggested was always correct.
Yeah.
I did wonder whether part of that is because what we're battling with at the moment is the low altitude of these
Yeah.
planets,
Okay.
and the fact that the images are distorted by the atmosphere.
Yeah.
In a way that isn't quite as simple as just grabbing the three colors and lining them up again.
Yeah.
Because the top half of the top limb of Jupiter is being bent by the atmosphere a different amount to the bottom limb.
Yeah.
In other words, it's not a linear bend. It's a curve bend. Yeah.
Yeah.
So I don't think Registrax will always get the right.
Okay.
Yes.
What amazed? Sorry, Alan. What amazed me was the final result from such a bad first picture.
Yeah.
Yeah.
And I can confirm that some of the video I've taken looked absolutely lousy when you played it back as a video.
Yeah.
See, I'm just wondering, the one I took last night, it seemed like it was up 3/4 of the way to the finished thing, just from the picture I took. Therefore, the processing side, I've really got to push to get the results. You know.
I've got Jupiter here, folks, where I'm about to lose it. So
Okay.
I'm going to share my screen if I can find it.
Let's stop my video.
Show window.
Okay, David.
Have you got that?
Yep.
Yeah.
So it's coming and going a bit. But that's a live image of Jupiter. A little white oval here. Turn the gain up. Ooh, I think we're losing it. It was lovely and clear the first 5 minutes. I think that cloud that Alan had has now made its way south.
That's looking good.
So as Alan said, we can crop the image. Or we can go the other way and get a tiny image. And should be able to pick up some moons in the wide field shot. So we've got 3 moons there at the moment.
You're videoing this at the moment, David?
I'm not recording it, but I'm just, I've recorded a few 1 minute shots, but it's just this ASI video mode.
Mm.
I'm controlling it through my iPad, so you can't see my fingers on the screen. But I'm adjusting the... We've had quite good seeing conditions the last few nights. I think it's deteriorating a bit now. I think that high pressure is a bit better now.
Mm.
That's
Do a
good
video
now.
of that. So
Yes.
now recording, you see on the bottom here, it's a number of frames per second. You want to really aim over 100 frames per second. Every now and then it slows down. And you want to aim for probably about 45 seconds to a minute's worth of exposure. So at the moment, this image has been stored on the little scan disk, little card that's plugged into the ASI Air. So when I image process it, I have to take that out and plug it into the laptop. So we'll stop there, press the stop button. So that's Jupiter.
Very good.
Shall we go and slew to Saturn? I should also say I'm also imaging it through an ADC, atmospheric dispersion corrector, which was set up for Jupiter. So because Saturn's in a slightly different position, it might not be optimized, but we'll have a go anyway. When you set up the ADC, you have a little, what do you call it? A little
Level?
spirit level on the top of it.
Yeah.
You got to get with the level with the horizon.
Yes, I bought myself one, David. I've started playing with it, but yeah, it seemed to work when I tried it.
Yeah, it does make a difference.
Yeah.
Yeah, I bought one too. This joining you lot has cost me a fortune over the months.
I think I'm probably going to need to buy one as well. Unless I can find a clever way of doing that processing as part of the image processing. David.
Well, in fact, it does work in Registacks, I must say.
Okay.
Yeah.
But do you know what?
But the other way of doing it is in AstroArt. If you let's just do it. If you do it in AstroArt, you can split the RGB up and align it separately.
Okay.
Yeah, we got Saturn there. Okay, let's go to video mode. Well, Saturn's a bit dimmer, so you have to increase the exposure and the gain. Just see the casino vision every now and then.
Yeah. I haven't used the video on ASI, so this is quite interesting.
So it's a bit of cloud problem every now and then.
Did you say, David, there's a new model of the ASI Air coming out?
Yeah, called ASI Air Plus.
Okay.
It has a little aerial on it, so it's got a bigger range.
Okay.
But my particular ASI Air is linked with is hardwired into the conservatory with a little Wi-Fi extender.
Yeah.
I should also say that when you're imaging the planets, you want to aim for the histogram to be sort of mid-range between 128 and 255. See, there's cloud coming over now, so we need to increase the gain. So the seeing's a bit not very good tonight. It's going cloudy, I think.
Yeah.
Okay, let's go and have a look. Do you want to have a look at Neptune?
Of course we do.
Yeah.
All right, not sure whether it's high enough up. We'll have a go. We'll go there. Might still be behind my trees, but we'll give it a go. When it takes a long time to validate it, it thinks there's probably a problem. How quickly does yours validate, Howie?
Quite quickly, if it's nice and clear, within seconds, 3 seconds.
Yeah.
You normally, maybe a little bit longer, if there's a light cloud. If there's a problem, then it's like this one. No, yeah.
Let's do a 10-second shot and see if we've got any stars.
Or trees.
Oh, we've got something. So the next thing we can do is we can press plate solve. Hang on, stop that. Yeah, it's having a bit of a think, isn't it?
Yeah.
Is that your focal length, 2479?
That's what it reckons it is, yeah. That's 9.
Is that with a hyperstar or is it just straight?
No, it's just straightforward C9 with an ADC on it. So there's no focal reducer or anything.
Yeah, okay.
I wonder, it doesn't look blue enough for Neptune, does it?
No.
Let's do a longer exposure. The other thing we can do is get the guider working. So it should now be guiding on that star.
Have you also got the position of the telescope on a sky chart at the same time, David?
No, I haven't got that software. I think you run it with Starry Night Pro or something, can't you?
Yeah, it's, Sky Safari. It
Sky
works.
Safari.
I can get that to work on my Esprit, but I can't get it to work when I also have the ASIA on the Mead 12-inch, but it doesn't work with it for some reason.
No, for some reason it's not plate solving tonight.
No.
Have you polar aligned recently, David?
No, I've only polar aligned when I set the thing up initially. It was, 6 months ago. But, I suppose I could recheck it.
Yeah, I do mine quite often, but it stays on line, in line quite well, I find.
Have you got the dew heaters on?
Yes, yeah, they're all on. So we lost a star, so it's probably clouding over.
I still
Let's
think
go back to Jupiter.
Just going back briefly to the man who let Jupiter drift right across the field of view. The other thing that crossed my mind is whether or not that helped in case there was any dust or anything or other problem. The fact that every image was then going to be taken on a different position.
That's an interesting point, Alan. Yeah.
Yeah.
Across the sensor. Because sometimes I've managed to take video, and for the whole clip, I've got a speck of dust on Jupiter, and the processing won't get rid of it.
Yeah, good point.
Because I didn't realize you could let Jupiter drift that far and still bring it all back and overlap the images. And that would eliminate all the dust spots.
Yeah.
It does depend on your magnification, though. I used to find with a little C4, Jupiter would only stay in the field of view for about 15 seconds.
Yeah.
As soon as you go to anything of greater magnification, it's just too quick.
Yeah.
Yeah, he did recommend using a 3x Barlow, didn't he?
He did, yeah.
It's like you want Jupiter to drift, but not at the normal Earth rotation rate.
Yeah.
If you could knock 10% off your drive rate temporarily, that would probably be enough, wouldn't it? So you get Jupiter to drift across the field of view in several minutes. That would be best.
Yeah.
I shall have a think about that.
I used to find with most of mine, it was jittering around so much in the field of view anyway, particularly if you reduce the field of view to sort of about 250 by 250. It's bouncing around so much, you're probably not going to get that sort of problem.
No, okay.
Don't you have various tracking modes on your mount? You have your lunar. Is it lunar? Solar?
Yeah, we could set it to lunar, couldn't we? That's a good one.
Or solar.
Yeah. So don't think solar would help, but lunar might be different enough.
Just
to make Jupiter drift.
Yeah.
Good thinking.
I keep having to adjust the gain because the cloud's coming and going.
Now we've got something on October the 4th, haven't we, Alan? With Jupiter.
October the 4th. What did I write? You have to remember, I didn't write that all in one go this afternoon.
Yeah, okay. Okay.
Yeah, what was it?
Jupiter colliding with the Saturn.
Rare chance to catch Ganymede and Callisto.
Oh,
Casting
shadow
shadows.
transit.
Callisto shadow begins transit from 1800 BST. Ganymede's 1950.
Yeah, because Ganymede's shadow always looks huge. It's probably not much different from the size of the red spot now, is it, David? Since the red spot's shrinking.
So I missed most of that video. Did he start off with auto stackert?
He picked it first, David,
Right.
and then he did auto stackert. Then he did Reggie stacks, and then he finished it off in GIMP.
Okay. Don't bother with I just go from auto stackert to registacks and finish off in either Photoshop, or I use, what's that smoothing program called? I've forgotten what it's called now.
Not
So
me.
the denoise AI.
That's right, denoise.
Yeah.
Yeah, I tend to use that, particularly if you've been using ISO 3200. Things tend to be quite noisy, and that gets rid of the noise very nicely.
You have to pay though, don't you, Mike, for that denoise AI?
Yeah.
I think it was fair. I bought it when it was on offer, and it was quite reasonable at the time.
Okay.
I don't know what it is now.
The moments are quite good seeing tonight, but it's shame the clouds keep coming across.
I'll blame Alan Green for that, David.
Yeah, you should have kept them up there.
Yeah.
David, can I ask you a question?
Yeah, far away.
I'm at the point now where I've got to take the card out of my ASI because I've got to fill it up. And it's the first time I've done this. And you mentioned some minutes ago that you take the card out and you put it into your computer. Then what do you do then? Is there a setup with ASI here? Or,
No, it's just like an ordinary memory card. In fact, I bought a second one, and I tend to fill them up every night. So, 60 gigabytes or something, quite easy to fill up with these videos. So then I download them onto a bigger memory stick. Well, I process them, and then rather than fill up my computer, I put everything, all videos on a memory, a big gigabyte.
Someone who's quite new to this, do I open up a program in the computer for, say, ASI Air for the photos, or? Oh
no! All ASI does is records. I mean, at the moment it's recording these as AVIs, which I'll process in AutoStacker. Or, of course, if you're just imaging galaxies, it's recording them as FITS files. So you just process each of those individual files, you stack them in your ordinary astronomy program. I mean, I use AstroArt. It's just recently been updated. I've spent a few dollars updating it. But yeah, I mean, that's wonderful. It will, automate everything from dark frames and flat fields.
Yeah, but with those FITS files, do you convert them first?
No, it's all processed in FITS files.
Oh, well, that's in AstroArt, is it?
in AstroArt. And then
Okay.
finally, you save them as a JPEG, and I'll finish sort of tweaking them in either denoise or Photoshop as a JPEG.
Yeah, I tried processing the FITS files from that in pip first and converting them to TIFF, but subsequent programs won't recognize the format at all.
Mm.
There must be some peculiarity in the way it generates the TIFF file.
There was I think an Italian observer noticed an impact on Jupiter last week. Bright white flash just after the Great Red Spot. There didn't appear to be any dark bruising like we had on Shoemaker-Levy 9 when that impacted Jupiter. But you know, you never know, these things do happen. There's probably been about 2 or 3 cases when impacts have been recorded on Jupiter in the last, or since Shoemaker-Levy 9 days. So I'll go and have a look at the sky and see if there are any other clearer patches out there. Well, Jupiter's the only thing I can see in the sky at the moment. I'm surprised we're getting actually any signal at all.
I think we're losing it, aren't we?
Sometimes a bit of cloud or thin fog actually helps the seeing conditions. Let's do another recording.
After seeing that other person's video this evening, you could probably get a decent image from that.
Oh, he's got no space left on device. So I can't record anything else.
I was going to say,
hard.
I was going to say, would it be possible to take us through you processing one of these files, David?
Yeah, of course. I tell you what I'll do. I will let me fire up my other computer.
Okay.
A good idea.
Well, it'd be interesting how he won it. We've seen the video. Let's see the final thing now. The final results.
I've got no one over here that I can go to, you know, and I need to see how it's done.
Well, I tell you what I'll do. I'll go out to the observatory and get the memory card out, and we'll process the images we just caught.
Okay, shall we have 5 minutes then for everybody to get a cup of tea?
Yeah, or a glass of wine.
Good idea.
Oh yeah, yeah.
Good
Okay.
idea.
All right. See you in a minute.
Right.
Cheers. I don't know how you do it, David.
Hello?
I don't know how you do it. I've got total cloud cover here.
Oh, it's gone cloudy now.
Oh, right.
Right, what I need to do is shrink that down a sec.
Got me cup of tea. Just in time as well. Oh,
Okay, can you share screen sharing now? Can you see auto stacker?
yeah.
So this is we'll go through some of the Jupiter pictures I took. This was Hopper State this evening, probably the first one I got. So we set this up for a planet. You click surface if you're doing the moon or the sun. Everything is fairly basic. I just leave all these as they are and press analyze.
Just to say, Howie, by way of explanation, David's starting with auto stack it. He doesn't need pip, but that's because his setup has produced an AVI file as its normal output. Whereas the guy in the video that we saw had a different file format.
That's right, yeah.
And auto stack it's a bit fussy. You're best to always give it an AVI file.
Other things you can do, you can press the play button and you can see it's align them all. So all those images, it has taken 4,300 images and it sort of aligned them. And what it does, it ranks them. So this is your quality graph. You've got the best at this end and the worst at that end. Normally I shall go around about, well, where the green line hits a 50%. So I can control click, say about that line there. So it's going to take 33% of those frames, of those 4,300 odd frames, and use that to stack them. Other options you can use the HST drizzle routine. If you've got small images, that will enlarge it by 1.5 times. It does something clever with the software. So once you've done that, you then place your AP, I think that stands for active point grid. I use about 48.
I think it's alignment point, David.
Alignment point, is it?
Yeah.
So that's enough, I think. Well, it's got 26 on. I don't think you want, I read some, I don't want to go too many. And then press the stack button. It's going to save it in a folder labeled 33%.
Just to say, David, I discovered that you've got 4 boxes there next to 3 more pink boxes next to the green one.
Yeah.
And if you're not sure what level of quality you want to use, you can put a range of numbers in there.
That's right.
And it will generate those files as all part of the same run, which can save a bit of time.
It will, but it will. Your computer processing will slow up.
Yeah.
Can I just ask Alan Smith?
Yeah.
If David had put that through PIP, would that have stopped that image juddering?
Not necessarily.
Okay. Okay.
The reason is PIP can also change the order of the frames.
Ah, right. Okay.
The judder could be coming because the atmosphere is juddering Jupiter about.
Yeah.
Or it could be because when you pick out the good frames, they appear randomly through that video sequence.
Okay.
And if it puts all the good frames at the beginning of the video, the effect will be that it appears to judder.
Okay.
But the juddering doesn't really matter because each time it has a new frame, it lines it up according to these points we've plotted.
Okay.
That's how it knows.
Yeah.
To lock them together.
Yeah. Now, looking at David's quality graph, it seems to me that the right-hand side, the right-hand box, has got the best images.
That's what it looks like it, but a lot of people have said don't pay any notice to the quality graph.
Oh, really? Okay.
It doesn't make sense. I don't think anybody's really understood, not even the developer, when he was asked.
Okay.
He was a bit vague about it.
Well, I think what that's doing is the jittery graph is almost plotting the quality of each frame in sequence through the video.
Oh, okay.
So you can see it's jumping about between each frame, good,
Yeah.
good, slightly worse, slightly worse.
Yeah.
It's a randomized kind of scatter.
So looking
But
at
the plot of the green line, the green curve rather, if you sorted those frames by quality, then now all the good quality frames are not scattered through the sequence, they're up the left-hand side.
Oh, right, okay.
And I think that green curve plot is, if you like, the quality height of each frame if we sort it in sequence.
Okay.
Okay. Okay.
So if
really,
you were to choose the 25% of frames,
yeah,
as David's pointing, you'll be including all the frames where the quality of those individual frames was all better than about 60%. Can you see? Because it's above the 50%
that's
line.
right. Yeah. Yeah.
If you move your bar further across, if you kept 50% of the frames, you'll be including all the frames that were better than about 40%.
Okay.
Now, the thing I don't understand is the pros and cons of how many of the poor frames you would choose to use.
Yeah. Because
you'd think the better image would come if you just chose the top 10% regardless.
Exactly.
And I know some people do that.
Okay.
I think you get
one of the things. Sorry, one of the things I found, if you run it through PIP, you can do a quality analysis, and it will order the best quality at the front end, and then that quality graph comes out a bit more sensible.
Okay.
Yes, it does. Yeah.
Okay.
So what we do now, go to Registacks. And that's the right file. That's today, half past 8. So click that one. Right, now, it's a bit of trial and error, really. I tend to start using the second one down. And if you slide it across, you begin to see it sharpen a bit. And the other thing I do is press RGB balance and go to auto balance. And you can play about with the brightness buttons. It's a little bit oversaturated here. So you don't want it to be bright white. The other thing you can do is increase the step increments or the initial layer. If it goes to 2, that might overcook it. But you can pull it back down using these sliders. Tend not to use the other ones too much. It's really a sort of a balance between not overcooking it. Anyone offer any advice as how they use Registacks?
I usually find I use the Gaussian rather than the default.
Oh, this one. Let's try the Gaussian then.
Yeah, because that then allows you to set how much it sharpens, and then you can denoise it slightly as well.
So I can reset.
But in those sliders, I very rarely use layer 1 because it's a bit harsh.
So we
Usually start at 2.
Layer 2. Do I go right along to the end?
I normally go to about 70% and then increase the sharpness from 0.1 up to, well, 0.15, something like that. Just keep increasing that until it starts to overcook it. Perhaps, yeah, a little bit more maybe, and then use the denoise just to get rid of any of the noise images. And generally, I find you know, the slider around about on 2, setting to about 70%, and then gradually on 3, 4, and 5 going down from 50, 40, 30%, and that gets a fairly nice even image then.
And do I raise?
You just fiddle with the sharpness, and then as soon as it starts to overcook it, back it off a bit.
Job to know whether you're overcooking it.
Yeah.
I don't know. Yeah, it probably looks better.
It's the I do find it's the most unsatisfactory part of the whole process when you don't actually know what values are even close to working.
Yeah.
And there's always that thought lurking at the back of your mind that if you'd only touched one of the other controls, you might have extracted a hell of a lot more detail than you actually did.
Yeah. The nice thing is, though, once you do get a good image, you can actually save the profile or save the scheme, so you can use it again.
What I do next is I'm not very happy with the color, but what I found, if I go to AstroArt now, that's our image we've just cooked. And if I go to color and I go to white balance, go to white point, I get a more natural looking Jupiter.
That's good.
So yeah, it's a bit of detail there. That's not too bad. So that's Jupiter. Let's have a look at Saturn.
I'd be happy with that.
So clear that. Open.
Where do you put that now, David?
Oh, well, I've finished. I always end up with my sort of final images. I put them in Dropbox. So here's Saturn 2047 tonight. You can zoom in a bit. You can, again, it's planet. So press analyze.
You're not going to use drizzle, David, for Saturn.
Yeah, we could do. I'll show you that. That slows it up a bit, but we'll do
Okay.
that because it's a bit smaller. Okay, place AP grid. Oh, it's only got a few. Let's put a few more in. That's all right. We're going to go drizzle, so we're going to make 1.5 times bigger. The quality graph looks a bit up and down. I'll probably keep it at 33, about a third.
Do you normally set the sharpened as well?
No, because I do that in Registax.
Okay.
I think a lot of people don't recommend using the sharpened in this.
All it does is produce a separate TIFF, doesn't
We'll
it?
end up with 2 images, but we'll do
Yeah.
that. So right, stack. The other button didn't realize I've ticked is RGB align. So I don't know how effective auto stack it is in actually aligning red, green, and blue.
Yeah, I don't think I've ever used that one, I must admit.
Okay, so it's now we go to Registax. So one of these is the sharpened.
The CONV is the sharpened one.
Sorry, which one?
The second one, CONV. Yeah.
Oh, right, okay. So let's start with the top one first, the normal one. So that's the settings we had, final images on Jupiter. So that doesn't look bad. It's got the Cassini division
Very
there.
good, isn't it? Wow.
So, okay, we'll leave it like that and we'll do all. And we'll save.
That's really nice.
Save that as Saturn. Now we'll do the second one. So this has already been sharpened.
Oh, wow.
So now that's
overcooked
cooked it a little bit.
Yeah.
My goodness.
Yeah, you can probably just denoise those sliders a wee bit.
The noise that's going up.
Yeah.
Yeah.
Yep. That's looking better already.
Yeah.
Yeah.
Oh, that's gone a bit green.
That's looking very nice.
Mm.
It's not bad for a bit of video through a cloud, is it?
Yeah.
So leave it at that, or can we do better than that?
Pretty good.
I'd be very happy with that.
I think that's pretty good, that, David.
Your
From that.
Well,
save image.
That's superb. Yeah.
nice shadow.
Now if I go
Really.
Yeah.
Astro Art file, open. So we'll open
Tidy up the colours a bit. Okay. Yeah.
buttons. So that's the convoluted one, or deconvoluted, I recall. Okay, so that was the sharpen with in a auto stacker, and that is the unsharpened version.
The sharpened does look a little bit better, doesn't it? Yeah.
Yeah.
Mm.
Yeah.
What we could do actually now is, let's save that. Right, if we now go to denoise, oops. Takes a while to fire up some of these programs.
Yeah, Photoshop seems to take a long time to load up.
Now we've got three different choices. Don't know if we'll use this before. Go to the standard one. And what you've got at the bottom here, you've got your enhancement. Just overcook it. So you see that looks a bit artificial. You've got the remove noise buttons, but when you overdo the noise, you lose the banding. So you want to take that right back down. Try it about a third.
If you increase the recover original details slightly, that helps with the banding.
Okay, yeah, might do. Again, that's probably I found on the planets, these need to be very lightly used. Well, no, that's, see, the actual noise has made that even a lot worse, isn't it?
Yeah.
Okay, this one looks, the low light one is actually quite good.
Just try the recover original details slightly, just see if you can get the some
On
of the
the
banding
standard
back in.
one.
Yeah.
Yeah, actually, I haven't used that before. That actually is quite
Does help, yeah. Trouble is, if you push it too far up, you lose all the effect of the sharpness and denoising.
Yeah. So this low light one, let's try and improve that a bit. Okay, the other one we're going to try is the clear one. This basically has 3 settings: low, medium, high, or lower, high enhancement. So this is quite a rough and ready one. It's a bit noisy there, so we increase and remove the noise. Still speckly. Yeah, that's not too bad.
That's better, yeah.
So we've got a choice: that one, or that one. What do you think is best?
I think the low light one, yeah.
Yeah, yeah.
Let's save.
Good night.
Save that one. So we have a final look in Photoshop. That's my full disk.
Where did you save the denoise?
It should be in here. Source, it should be here. Okay.
Yeah.
That's right.
That's it.
So it's not bad. We've got the Cassini division. There's a bit of banding, but probably the best Saturn I've taken this year. So that wasn't too bad.
Very nice.
Let's have a look at Jupiter. course, there's filters in Jupiter as well, but sorry, in Photoshop. What I tend to do, if you keep, as long as you keep the radius below 1, and then follow that with a median filter, a radius about 1. Not up to Damien Peach standard, I'm afraid.
That's pretty good.
Yeah.
Very good.
Yeah, I think so. I'd like to have something like that.
Well, I'm sure you get that in the Pyrenees. The planet's a lot higher down where you are.
Yeah.
A bit closer.
Yeah, we're closer to it. Yeah. Yeah, it's true. And you record every sort of Friday night, don't you? Could I see this again through Peter? You know,
Yeah. Kerry used to send the links out. I mean, I'll remind me of your email address, Howie. And
do you want me to get Pete Yao to send it out to everybody?
it's so interesting, so useful.
Yeah.
yeah.
It's just what I need, and so a lot of others.
Oh, it's Alan.
Well, I'll tell you
Mike.
what, Dave. Ask Pete Yao to send it out, but we've requested if people want to join in for our live imaging session, the more the merrier.
Yeah.
So Howie, could you do it from the Pyrenees?
Well, I'm sure I'm trying to set this up. This is what I've been doing over the coming months. You know, I've put I've put the Wi-Fi system in both observatories. I can link in with Peter. All I've got to do is start to transfer photos onto my computer and know how I can share the screen with you, so that from here I could do a live view too.
Yeah, that'd be good. Mike, can you live image?
I can, but the problem is at the moment I can't handle the mount and so on down the steps.
Right,
into
yeah,
the
cool.
garden.
Yeah, disposable.
It's only been 4 weeks, so
don't risk it.
but hopefully in the next couple of weeks I will be able to, which is getting a bit close, but yeah, I'll have a go.
Do we want to try and schedule another attempt next Friday, David?
Yeah, yes, of course. I mean, what you could do, Mike, can you live image from, say, a DSLR on a tripod?
Yes, I could probably. Yes, I don't see why not. Yes, just on the. And use the
star field, and you can talk about where the planets are in the sky and like that.
Yeah, and I've got the Omicron, clockwork mount.
Oh
thing.
yeah, that was.
So yeah, I can probably do that. That's no problem.
Yeah.
Okay.
It's just the heavier equipment I can't shift at the moment, but I'm getting there.
Yeah.
Okay. Sounds like we've got a plan then.
Great.
Okay, good.
When is the date for live imaging then?
12th, 13th and 14th of October from 8 o'clock. Weather permitting.
Righty-ho.
Okay.
Yeah. Okay. Well, I personally found that very interesting tonight. Thank you very much, David.
Yes, thank you.
It's been excellent.
Everybody has a different routine to it, and share what we do. Then
yeah,
some might work,
very
some
useful.
might not.
Okay,
Thanks,
everybody.
David. I learned a lot tonight. Yeah.
Good.
Yeah.
Much appreciated.
Okay, so yeah, I'll get the links to Pete and yeah, get him to send them out to everybody. Yeah.
Dave,
Thank you.
did you get the that copy of Photoshop I gave you the link to?
I haven't done it yet. I've been up at Mother's. I got back on Wednesday, so
Okay.
still sort of out.
It's the same program David was using just there.
Yeah, I guess so. Okay.
Yeah. Okay.
All right. Okay, thanks everybody. Good night.
Thank you very much.
Be in
Good night.
touch.
Thank you, everybody.
Good night. Thanks, David. Brilliant.
Thanks, David. Bye-bye.
Brilliant.